Going to introduce roots and radicals under topic 18, page 97. And on page 97, in this video, we're just going to look at three things. The definition of what a root means, multiplying, dividing radicals, and adding and subtracting radicals. So let's go to the definition. And the nth root of A is denoted by the radical. We'll explain what this means, make it a lot simpler, where we'll look at this particular calculation and show what it means. So, first of all, n is called index, and A here, n is the index, and A is the radicand of the radical. Don't worry too much about the terminology, the emphasis on the meaning. So what we can do is we can view roots as the opposite of applying exponents. So for example, 3 squared is 9. What does it mean when we write 3 squared? We mean 3 times 3. 3 multiplied by itself twice. Okay? And so the opposite of this would be to say, okay, the square root of 9, put a little number 2, put the 9 here and say, what number when multiplied by itself twice would give us 9, and the answer is 3. The term square root of 9 can be read as the square root of 9 or root 9. So when there's a little number 2 up here, we refer to it as a square root. We can also just say root 9. The square root of 9 is often written as this. So when we write this, it's the same as this. We just don't put the little number 2 here, because it's implied. If there's not a number up here, it means that we're talking about the number 2 and a square root. Now let's take to a little more complicated case. 5 cubed, or 5 to the power 3. Cubed means 3. So 5 to the power 3, which means 5 times itself 3 times, or 5 times 5 times 5. That's what 5 cubed means. The opposite of this is to say the cube root of 125, and 5 multiplied by itself is 3 times is 125. So the opposite of 5 cubed is taking the cube root of 125, which is essentially asking what number when multiplied by itself 3 times gives us 125, and an answer is 5. The cube root of 25 can be viewed, when I put this little number 3 here, can be viewed as the cube root. So the number 3 is synonymous with the word cube. If we take 2 to the 4th, we know this is 16. Why? Because we're multiplying 2 times itself 4 times 2 times 2 times 2 times 2. And the opposite is to take the 4th root of 16, which gives us 2. So 4 can be read, 4 outside here is read as the 4th root of 16. So to review a little bit, when we don't put any number up here, right in this corner here, right up here, that means it's a square root right here. The number 3 can be referred to as the 3rd root. Yeah, you can say the 3rd root, but it's more common to say the cube root. Once you get above 3, you actually just use the numbers themselves. 4th root, 5th root, 6th. Now, note that the value of the simplified radical is positive here. When we take this, the answer is positive. While either plus 2 and minus 2 might have been an option to get squared to get 4, you're trying to find all the possible values that might have been squared to get 4. So you could use plus 2 and minus 2. But when you are simplifying this expression here, the only answer is 2. This positive result is called the principal root. So x squared is 4. The possible answers are plus or minus 2. But when we actually do the square root operation, okay, then we only use the principal root or plus 2. Now, if we go back to the top of this page, we're going to look at this expression here. The nth root of a powered to n is equal to a for integers n equal greater than or equal to 2. So what does that actually mean? Let's go down and look at what that means. There's actually 2 operations here. First of all, we have to take the nth root of a. It might be the square root, it might be the cube root, it might be the 4th root. And if we apply that same as a power rule here, we're doing the exponent rule right here, then essentially the 2 operations cancel each other and we just get whatever is here, right here. If this and this are the same, then the answer is A. So I know that's maybe a little confusing, so we're going to break it up. And by the way, n has to be greater than or equal to 2 here. So first of all, we're going to realize that there are 2 operations to perform. We're going to perform the operation inside the bracket, which is this one here, which requires us to take the nth root of a. So this is really n square root of a, nth root of a, I should have said not square root, nth root of a. And implied here when we write a is 1. And when we take the nth root of a to the power 1, we put the n on the denominator here. So it's 1 over n. So if example, this would be 2, we put the number 2 here. If this was the cube root, we'd put the number 3 here. So that's the first operation that we are doing right here. So when we have this, there's an implied 1 here, and we divide that 1 by whatever this number is here, and we get that. Now the second operation, which is whatever happens as a result of this, the second operation to the nth power, which is this one over here, requires one to take the answer from the first operation, namely this one, and multiply it by itself n times. So we take this one, we put it over here, and then we multiply it n times. So this operation here has given us this inside the brackets. Then we have this, we replace this as n over 1. Well, 1 times n gives us 1 times n, and n times 1 gives us n times 1 here. So we're just multiplying the numerators and the denominators. And notice the n's will cancel. We get n over n because 1 times n is n, and n times 1 is n. N over n is 1. A to the 1 is the same as a. Let's take a look at some specific examples. So first of all, the overall result of this is that the first operation is reversed by the second one. If we go back over here, the first, whatever we did here is reversed by here, and we're left with A. So let's look at an example here. We've got the 5th root of 32. Now remember what I said, instead of 32, we write 32 to the power 1. That's what it means. If I just write 32, it means 32 to the 1. We're taking the 5th power. I said you take this number and divide it by that, which is what I did right over here. This is this number here, which is 5 over 1. So you can see what happens here is you've got 1 times 5 over 5 times 1. So you've got 32 to the 5 over 5, which is 32 to the 1, which is right here. So you can see the first operation has canceled the second one. So we take the first operation again, requires us to calculate the fifth root of 32, which is 32 to the 1 over 5. That's this operation right here. The second operation, which is this one right here, requires that we take the 32 to the 1 over 5 and then calculate 32 1 over 5 times 5 over 1. We'll see the 5 cancels with a 5, and we're just left with 32 to the power 1, which is 32. Now, multiplying and dividing radicals. So you can see here, this term is called the index, and n could be 2, 3, 4, okay? And what happens is that when you multiply these two together, as long as the index is the same, you can multiply what's inside the radical. So you can multiply the a times the b if the index is the same. So what's an example of that? Well, if we have the square root of 3 and the square root of 2, we can multiply the 3 times the 2 and get the square root of 6. If we've got the cube root of 4 times the cube root of 7, you can take the cube root of 4 times 7, and you get cube root of 28. Now you can't multiply the cube root of 5 times the fourth root of 5, fourth root of 6, because the index is different here. Here, this index is the same as that one. This is implied 2, this is implied 2, and this is implied 2. So, as long as the index is the same and you're multiplying, you can just multiply the terms inside the radical. And here, if you have the nth root of a over the nth root of b, you can simplify this by just writing the nth root of a divided by b within the radical. So, for example, if you have the square root of 6 over the square root of 5, you can write this as the square root of 6 over 5. Similarly, if you have the fifth root of 64 over the fifth root of 7, you can combine this under one quotient here and then take the fifth root. This means the fifth root. Now, there's no number here because it's implied 2. So this means that the index is 2, this is 2, and this is 2. When the index is 2, we don't have to write it in. Now, you can't combine these two under one quotient because this has an index of 3 and this has an index of 5. Okay, adding and subtracting like radicals. We've seen how we can multiply like radicals, but what about adding and subtracting? Here we have 6 root 3 minus 4 root 3, and that equals 2 root 3. Why? Well, we can factor out the root 3 term. If we factor out the root 3 and use the distributive rule, 6 times root 3 gives you 6 times 3, 6 root 3. And minus 4 times root 3 gives you the minus 4 root 3. So all we're doing is factoring out the root 3 and using the distributive rule. 6 minus 4 is 2 root 3. Now, notice you can only, these are both have the same index, and the radicand has to be the same here too. So you've got to, you can't, if this is 4 and this is, excuse me, let's use another number not to confuse it. If this is 5 and this is 7, you can't do anything. So the radicand here has to be the same. So we factor out the root 3 because it's common to both these. Now, you could say let x equals root 3. So this is 6x and this is 4x, which gives you 2x. Well, if the x is root 3, you just replace it. That's another way of looking at it. Now, here you have the same index. You have cube root of 17 minus 6 cube root of 17 minus 4 cube root of 17 equals this, y. Okay, we factor out the cube root of 17 by the distributive rule. 1 times this gives me this, minus 6 times this gives me that, and minus 4 times this gives me that. So now, 1 minus 6 minus 4 is 1 minus 10, which is minus 9. I usually put this in the front, not afterwards. So I got minus 9 cube root of 17. This is applying to this. It has nothing to do with a 9. This little 3 is a cube root of 17. So you can't add root 4 and root 5 because the radicands are different. This number has to be the same as this number. You can't subtract these two because the indexes are different. Here there's a square root, here there's a cube root. So this, we've discussed the first 3 topics on page 97. The next video, we'll go back. Let's go back 1, 2, 3. Okay, we've discussed this, we've discussed that, and that. So as the video is not overly long and there's a number of new concepts, next thing we're going to do is rationalizing denominators and the definition of rationalization.